My name is Mohammad Adibuzzaman. I'm a research scientist at the Regenerative Center for Healthcare Engineering located at Purdue University, Indiana. Before I start, a little bit about my background. I'm a computational scientist by training. My undergraduate degree was in computer science. My PhD was in computational sciences. But primarily I worked in healthcare in different projects with my advisors in FDA and physicians. So this presentation is about my experience with different healthcare projects and what should be the ideal computational platform look like, what are the methods that we need, in my opinion, to address some of the big challenges in healthcare. So I will start with a few use cases. Those are two different healthcare-related projects that I have worked on over the years. The first one is about hemorrhage detection. So I will actually repeat many of the talking points that the previous speakers have told. So bear with me in terms of the data platforms, but this might be a little bit different from the other speakers. So hemorrhage detection is the project that I worked on during my PhD years and is still continuing on this project. So the basic idea is when you have internal hemorrhage, your heart rate goes up, your blood pressure goes down. Here in this picture on the red vertical line shows that the starting point of hemorrhage. And as more and more blood is being lost from the body, your body tries to compensate by increasing the heart rate so that the blood pressure remains constant. But this is a major problem in clinical settings because physicians cannot really understand if the person is going over internal hemorrhage only from the blood pressure data because the way body reacts, because the body compensates in a way that it tries to stabilize your blood pressure data. So there are some statistics about hemorrhage and acute hypertensive episode, that is the eventual outcome of hemorrhage, which is, this is one of the major reasons of pre-hospital deaths and first 24 hours deaths after trauma. And existing systems actually use a method called shock index, which is just the ratio of heart rate and blood pressure. So if the ratio increases, it means your body is not able to compensate the blood loss. And that is the way physicians actually try to find some clues about ongoing hemorrhage. Here is an algorithm that is based on compensatory reserve index that is developed by US Army. And they can't really take bloods from humans to build the models. So they try to simulate the hemorrhage in healthy subjects. So here is one example of how to do that. So they put your body in a lower body vacuum chamber so that your blood is sucked down on the downside of your body, and your upper body loses blood volume. And that actually reflects some form of simulation of a hemorrhagic situation. And at that time, they try to capture all the vital signs to build the models. This is also a very big problem in battlefield situations, like how to triage patients. So during my FDA years, I started with animal study, not on humans. So these were immature swines, which is pigs. And they extracted bloods for 7 swines until they died. And during that time, they captured all the vital signs, heart rate, blood pressure, ECG, whatever, pulse oximetry, every vital signs. And they gave us the data and said, build us a mathematical model where you can tell from the blood pressure data that the pigs were being hemorrhaged. So this was the model that we developed. My advisor was a mathematician. He was a big fan of Markov chain. So I was playing with those tools, and these are fancy methods from a physician's perspective. So what we did was we just used the blood pressure data and developed a Markov chain by identifying different range of blood pressure as different states, and then try to find different characteristics of the Markov chain over time to see if progressive hemorrhage is causing any change in the hemorrhage, in the data. So this is the results that we had from that study. These, again, the red vertical line indicates the starting point of the hemorrhage. And we came up with a parameter called mixing rate, which is the second largest value of the Markov chain. And we saw that over time, as the hemorrhage progresses, for different colors, you actually have different peaks, that mixing rate changes almost consistently. And we showed that this is a very good number to detect hemorrhage. And the correlation coefficient with shock index, which is the standard measurement for measuring progressive hemorrhage in the healthcare current settings, it showed a very good correlation coefficient, which was 95. Now, I was very happy about that, and I thought I solved a major problem, but it was nothing close to what needed to be done. Now, the next question was, how do you know this works on humans? Now, I did not have access to human data, so I was looking for opportunities how to get human data. So there was a Computing in Cardiology Challenge in 2009, and this is organized by Roger Mark every year from MIT, and they provided some data of acute hypotensive episodes, which is the extreme case of hemorrhage. So they defined an acute hypotensive episode where you have 30 minutes or more of time, blood pressure data, and during that time, 90% of the data is below 60 millimeter mercury pressure. Now, that is a definition came up for the challenge competition, but it doesn't necessarily mean that the patient actually underwent hemorrhage. It could be for something else. So your ground truth is actually not as solid as we thought. But let's try that. How about, let's see if it works on that patient data. Now, here is the MIMIC database. This is over 10 years of data for 60,000 hospital admissions from Beth Israel Deaconess Medical Hospital. They collected everything: electronic health records, pulse oximetry, continuous waveforms, everything. And the first part on the left side, you have clinical database, which is in Postgres, around 40 gigabytes in size. The second part, which is the waveform database, that is the physiological monitoring data that is captured from the bedside monitor. And that size of the database is around 50 terabytes, uncompressed. Now, I did not have the computational platform or the high-performance computing systems at Purdue at that time, and I did not know how to do that. So I actually partnered with Marilyn Match and Paradigm 4 and tried to load the entire waveform data from the match subset in a small cluster at Purdue, and then try to set up the environment to actually run the algorithm. Now, one key thing here is that the match subset, why do you call it match subset? So each waveform record has a corresponding patient ID, and that is all you know about the patient ID, about the patient. What it means is you do not know what was the name, what is the age, gender, admission type, what is the diagnosis. You don't know anything about the patient from the waveform database alone. You must link that to the corresponding clinical database. And they only did that for 5,000 patients. So from the Computing and Cardiology Challenge data, for the 60 records they provided, we found the longer waveform from the match subset, and then found the corresponding clinical information, which is the diagnosis, clinical notes, age, gender, other information from the clinical database. So as you can imagine, this is not a very fun thing to work as a data scientist. You just want to plug and play and use these tools with the drag and drop options. But we had to build all this by myself, with our students and myself. So here is the problem. From once we have the waveform database, we define the problem like this. We have a 10-minute observational window, and you have a 60-minute forecast window, and with that 10-minute observation window, you try the algorithms to see if it actually works on humans. So this is the results that we got from the human subject. And the blue line actually shows the average of all the humans. And the the gray lines show each individual humans. And here you have, as you can see, a lot of subjects actually did not work, but for some subjects it did work. And on average, it worked. But this is not how physicians work. You have to explain them why it works for which patients and for which patients this algorithm will not work. So this is where we are right now with this project. After 2 or 3 years of working on this project, we still could not claim that this algorithm works for all humans or any particular diagnosis, but we are at a point where we can claim that for some diagnosis, this doesn't work. And that diagnosis was gastrointestinal bleeding, which is a specific hemorrhage. So this is the points that I just made. So algorithm works for some patients and for some patients it didn't work, but the question is what are the characteristics of the patients that actually make the algorithms work? And that is a critical thing for the translational piece. So this is one project. And I will jump into another project right now, which is stroke risk stratification. So I'm talking about these projects to show you what are the hurdles that we had to go through in terms of collaborating with the physicians and the translational aspect of data-driven algorithms in clinical practice. So this project is motivated by this problem, which is if someone has atrial fibrillation, they have a higher risk of stroke. And physicians use a scoring mechanism based on particular characteristics, which is called CHAS score, which is congestive heart failure, hypertension, age, diabetes, and previous stroke. So those are the features that look into, and they characterize each patient's probability of a second stroke based on those characteristics. So for this study, we just started this study. We again looked into the mimic database, and we had limited access to the data. And stroke is not actually not all patients with stroke end up in the ICU. Only 10% of patients who have a stroke end up in the ICU. So if we develop a model based on intensive care unit data, it does not reflect the practical scenario of stroke patients. But still, we wanted to do some preliminary results so that we can apply for our collaborators, apply for more data from our collaborators. So mimic database, we looked 46,520 patients, and with a diagnosis code of ICD-9, diagnosis code for atrial fibrillation, we had around 10,000 patients who had atrial fibrillation. And then you have several inclusion and exclusion criteria based on the physician's requirement. For example, we excluded all the in-hospital deaths because the time period for predicting stroke, if you already died in a hospital, is too small, so that was excluded. And also patients with anticoagulants were excluded for this study. And finally, as you can see, we had a very small cohort with true stroke positive, which is only 28 patients. And most of the patients actually did not have a stroke who already are diagnosed with atrial fibrillation. So these are, but still, to generate this cohort, we had to write a lot of code and using SQL and then from SciDB using AFL language. So here are some existing scoring mechanisms that use different features. As I mentioned earlier, CHAS score uses congestive heart failure, age, diabetes, and there are some existing other scoring mechanisms as well. So CHAS-2 is the most popular scoring mechanism, but we tried to extract all the features that was collected in the intensive care unit and to see if those algorithms can actually provide better result than those scoring mechanisms. Here is our initial result. So here the gray vertical line, gray bars show the CHAS score performance. The brown color shows training performance, and the yellow color shows the performance or the validation score. And the training performance was pretty good, as you can see. The Y score shows the proportion of stroke, patients who are actually had a stroke, and the training said was actually overfit because of the small sample size, and the testing said fails miserably. But at least we can now apply for more data from our collaborators to see if we can actually build this model over more samples. So the challenge here for this particular project was ECG data was in SciDB, which is needed for atrial fibrillation detection, because if you diagnose atrial fibrillation from ICD-9 code, ICD-9 code is not the best measurement for any diagnosis, because these were mostly for billing purposes. Then some features needed to be extracted from the echocardiogram data, which is the ultrasound imaging, and we did not even have access to the data. And features are structured in SQL. So these are different database technologies that we are trying to get different features, and also the massive amount of data was a challenge. So the question that we were dealing with all the time is, how do we streamline this entire data collection and feature selection process so that any student that I work with can ask these questions in a matter of days, not in 6 months or 1 year. So this is the general pipeline for existing publication in healthcare, which is you at first identify different cohorts, you then integrate and then de-identify, and there are some data broker that you usually deal with, and then you have to go through IRBs and then put that in the high-performance computing environment. And finally, you may have some analytics and then maybe some publications. And this is a big bottleneck for us as researchers in healthcare, because we don't want to deal with the pre-processing and feature selection process so much time on that. So these first two steps, which is big data pre-process and high-performance computing, are two of the major bottlenecks that we are dealing with. And this, as this community already knows very well, that this is a very common problem in healthcare, and we don't really want to deal with those problems. So we developed a computing platform with a small cluster and put the entire mimic database to develop all these projects that I just talked about. This is just 2 of the projects. We have around 10 more projects in our center. So anyone can remotely log into the system, have a code repository, and once you have some analysis done, you can share that code as a digital object or an app, and anyone else can just build on top of that. And this is a common talking points for this conference. So we did that with the mimic database and only the matched subset, and even with the matched subset, we had around a few terabytes of data for the ECG. So with the mimic database, we use this platform, Postgres for clinical database, and this is the existing waveform technologies that are being provided by the Roger Marks group from MIT, and existing systems don't support the high-performance computing systems, feature selection approaches, cohort selection, and these are complex queries. You cannot just drag and drop different features because every clinical problem is different. So how do we provide a framework for computer scientists where you don't have to write every piece of code? If someone else has written it anywhere else in the world, you can just reuse the code. And this is a list of publications from the mimic database. There are at least 1,000 publications that use mimic database. And as you can see, most of the publications uses only the clinical data, which is reflected by the second to last column, data, C. So which means that most of the publications could not use the waveform data because of this complexity of analyzing the waveforms. So the match was not there. So even if the data was there, people were not able to use it because of the existing infrastructure, and the translation piece is another big hurdle, that is why some algorithm works, the explainability part. So our system architecture, we used clinical database for Postgres, SciDB for waveform. For integration, we just used R on top of these two different languages, and for visualization, we use Shiny, which is a JavaScript API on R. So these are just the basic steps that we had to go through for our architecture. So this is an in-house development, and Paul Brown actually load the entire match subset in the SciDB infrastructure here. So I'll just show one demonstration of our platform. So here are all the users, as you can see. So don't be judgmental. This is very naive way of doing internal research works. So these are around 24 or 20 users that we are using the system. And if you select any individual user, you'll see that there are multiple projects that are organized by that particular user. And if you select any particular project, the entire work from raw data generation to visualization to inference would be reproduced real time from the system. And that is, and if a new researcher comes in and he or she just wants to test a different hypothesis or build a different algorithm for his specific research problem, they can just tweak one or two lines of the code instead of going through the entire process. Finally, I will just finish by saying that this is not even close to build the ideal data platform for our system. So we actually just submitted an NSF proposal on this concept. How do you provide a computational platform that supports reproducibility both from algorithmic and database perspective? And the algorithmic perspective is very, very important because from my experience at the FDA, physicians do not buy even if your algorithm is 99% accurate. They will ask you why it works, why it doesn't work, can you explain that? So how do you provide the causality of your output of the algorithms and transportability and generalizability of your findings? Because even if you have some findings from a 1 million patient cohort, does it mean that it will work for everyone? Or is it only work for patients from California? It will not work for patients in Alabama. So how do you find those issues? So that is a topic of another discussion. So I'll just stop here and take any questions.
Let me start things off by asking, with regard to your last point, in order to get explainability of the results, does that limit the selection of algorithms that you can apply to actually identify features and do any kind of learning on the data, any kind of modeling?
I don't have any right answer to that, but I have my opinion. Yes, it does. So what right now I'm working on is a structural causal model, which is the graphical model that represents the relationship between variables, and that also provides that can also learn from the data. So it provides both the domain knowledge that is built in by the physicians, where the spurious associations that comes up from machine learning algorithms are extracted, and then that structural causal model can be used to enhance the physician's understanding of the problem from the data. So I would say yes to that answer.
Okay. Or maybe another way of getting at it, I guess, is that even if you've, let me say that even if you've managed to learn something very well using some model, is is there a way that you can turn that into some explanation externally?
Yeah, so that's
Even if within the model you can't explain.
Right, that's a very good point. And most of the hypotheses are actually generated this way. And then you have further investigation down the line then that's why you have different levels of randomized control trial. But those are very expensive, and you don't want to do randomized control trial because that's the benchmark for establishing causality to understand why it works and why it doesn't. But how do you actually use these millions of patients' data and do a virtual randomized control trial by removing different biases that are actually the true reason for doing randomized control trial in the first place, which is confounding bias, sampling bias, selection bias. So that's the methodological challenge, and this domain is still very open and not matured enough in this big data revolution. So I think there are much opportunities in that domain as well.
Well, one final question. When you said that you're limited by the amount of clinical data that you can actually get access to. Mm-hmm. When you actually get access to large amounts of data, mm-hmm. Many more ECG trace and waveforms, do you already have plans for how you're going to scale your system to those levels?
That's a very good question. So I do have some plans from our university perspective. Purdue has started a big data science initiative, and we are collaborating with the team. And I also think that eventually there will be bigger companies than Google, Microsoft, and 23andMe, those companies that would actually do this healthcare data analysis for personalized recommendations, social network sharing analysis, population risk analysis, everything together. So I think that industry is just going to develop at this point. It's a very nascent stage, and in 10 or 15 years, I don't know who will be the leader in that domain.
Okay, thank you very much.